part 2, and hopefully took a break. This is sinuous hair eliminator, and they eliminate the need for stables. Again, now we're talking about ways to maintain the tubes in place, because probably you've seen a radiator that's been plugged or been squished, and once the tube are out of place, the water inside the tubes will not run efficiently, and the combustion air or the heat exchanging air is not running the way it was designed for, to carry the heat out of in the radiator. So in here we have many ways to keep those radiators in place. Either we have stables, or we can have sinuous, we can have membrane. For example, I can show you a radiator here. So if we look at this, it's kind of a baseboard radiator. If we look at the fins over here, and if we look at those little tubes. So we need something to keep those tubes in place and enable us to circulate the air through the tube. So these spaces are calculated accurately to maximize the heat exchange and the efficiency of the boiler. So these are some of the things that we can, some of the symbols we can use to maintain the spaces between them properly. Here we have something called baffles that are used to direct the gases of combustion so that they can come close to contact with the boiler heating surface. By heating surface we mean the tubes and whatever is between the water and the combustion air. So baffles, if you can see, these are the baffles here. See? So we can have the air go this way first, it turns around, then goes outside. The more turns you give the air, the more heat you can absorb from this hot air. And again, we have to be always very careful. We have a design temperature for the combustion air and a design temperature for outside the outlet of the air, because we don't want it to be too cold. But at some point, if it gets too cold, it will start to condensate, and most of the condensate will be very, very acidic. We'll talk about that later on. Here we see a water wall extend, refractory life of and increase the steaming capacity of boiler. These water walls actually are placed next to the pipes to eliminate the heat escaping the chamber. So you want to have your boiler chamber, and you have some kind of barrier to support the tubes and also to refract the heat. So on economizers, what is an economizer? From the name, I will guess it's going to save me money, right? It has to do with economy. So what it does, I'll read you the definition. So an economizer consists of heat exchanger that use heat from the gases of combustion to preheat feed water. Economizers improve overall boiler efficiency because this heat would normally be lost up the stack. Let's think about it. Remember what I told you earlier, that you don't want the heat coming out of the outlet to be too low. You want it to be cold. So let's say we're firing too much gas inside the chamber, but the air coming out is too hot to be dispensed, to be ejected to the atmosphere. And there's some useful heat that we want. So we can use that heat to heat the water coming into the boiler. So the boiler is not coming at 40, it will come at 150, so it's ready to be evaporated. So that will save me some money by capturing all the heat that's leaving the boiler. So these are some of the what's called packaged boilers, which means they are already made and you can buy them as is. So you cannot really specify what temperature you want them to be, regardless of what kind of operation you have or what kind of need for steam you have. They are some kind of packaged boilers. So they're sold based on BTUs and also based on the space. Another example of stage and how you can keep the tubes in place. This illustration is showing you. And here they try to tell you how they make the tubes. That's none of our concerns. How they make them and bend them. Of course, there's a lot of processes and treatment involved in the process. But again, it's not up to us to design it. We just accept the design and know what are the limitations of that design. Again, some of the examples, where do we use boilers? Refineries. I did work in a refinery for a while. and refineries they're a major user of steam. Why? They have to heat the product, which is crude oil. They have to they have to generate electricity. So they use steam for heating, for cleaning, for stabilizing the product, and also for generating electricity for the equipment that runs in the refinery. Where else? This is what we have for power generation. We have a big generator that is connected to a turbine, and that turbine is connected to a steam boiler. The steam will push the turbine wheel, and the turbine wheel will push the generator, and eventually we'll have power being produced. So let me just reiterate here. So we have a steam boiler. Let's see, this is our steam boiler. So we have a big fire here, steam coming out. We capture that steam. It goes into a big turbine. So the steam will hit the turbine. It will start to spin. Imagine this is the inside of the turbine. It starts spinning. This shaft is connected to a power generator, which will have a big rotor that will spin. And by spinning, it will produce electricity. This is how we produce electricity these days on mega scale. No matter where you go for any big power plant, they are using this simple, well, it's not simple, but it's very common technology, but it has not changed since I don't know what, the 20s. It's been there forever. Yes, we do use solar power or hydropower, but again, with the hydro, we use, again, instead of the steam generator, we're gonna turn the turbine using water flow. For wind power, and instead of the generator, we're gonna turn the turbine using the blades. So eventually you will turn a blade using mechanical power into electrical. This is the most common way to generate electricity in mass scale. Photovoltaic, which is the cells you see on rooftops, those are producing different kind of electricity, and it's not as in big scale, mostly small. For power generation, this is how we distribute the power. We have a power bank or the power generation, and it will go into smaller and smaller scales until it comes to your house. So there's a big kilovolt station, substation. It steps down, and every time again we go further or smaller, we lose a lot of energy. So this is basically what is the distribution of power looks like. Switches, again, we don't have to worry too much about this, but basically these are switches transfer power between normal and alternate power sources. Again, you don't have to worry about that a lot. I don't think it's going to be in your quiz, but just to know that how do we switch power between one station to another. Transformers, probably you've seen these in your neighborhood or district. We have some here in the lab. They are used to step up or step down, or sometimes isolate voltage. So you get like 4,000 volts. These will transform the 4,000 volt into 400 or 120. So you'll see probably one for each neighborhood. Conduits is where we protect our power distribution. So we have to have very reliable power transportation, and of course inside the conduits you always see a lot of wires. So these are like categorized based on the size and the amount of voltage that runs through them. More distribution, we do not care much about that. Probably you'll see this in a power plant. It's where you have disconnect switches, and if you take a course in electricity, probably you understand what these wires mean. For our intended process now, we're not going to focus on the wiring per se, but if you take the theory and control course, we'll talk about power distribution and what are these legs meant to do. This is some centralized power connection. This control is for a boiler, and you can see all these switches that control the boiler. We'll talk briefly about those, but the connection of these controls has to be done by a professional who has been trained on this kind of control. So this control here, it's called PLC, which is programmable logic control, which will control the boiler operation between like pre-purge, ignition, main fuel, main flame, then post-purge. So yeah, eventually, in just to cap out what we have, we learned about the type of boilers, what do they do, what do we have in terms of fire tube and water tube, what is the differences, what is ASME categorization for the stamps, and who designed them and why. So please read chapter 1, try to do the homework at the end of the chapter, and also if you look in your study guide, you might want to try to do the problems in chapter 1. There's an easy efficiency applied math that I'll try to touch base on. So these is it here? Okay, we got it. So if you look in chapter 1, you'll see all these review questions. Please try to go over them. Some of them will be in the quiz. If we look here, I think this is what I assigned in the syllabus for applied math. I'll go over both of them and try to explain what do they mean, how it's done. So in this, so the horsepower and efficiency, actually, I don't want this one. I don't know if it's on our side, it's the one side here. So heating surface, so we talked about boiler efficiency and how much we have, the more tubes we have, the more efficiency we have, and we said that it's based on surface area. So what they're trying to do here, which is very, very simple, you can read through it, but I'll give you an example. Let's say we have a 4-tube, 6-tube boiler, okay, 6 tubes. And we want to know what is the surface area. So, okay, we're gonna try to estimate the surface area. If I have a cylinder, which is a tube, what would be the surface area for this tube? This will be the circumference of this circle, which is pi d, which is the diameter here, multiplied by this length, which if you open up is going to be a square. If I took this can or something and open it up, it's going to be a square. So this is going to be my area for one tube. So pi d is the diameter, and area, actually this is the length. This is going to be the length times the length. This is going to be the area. So this is going to be my area for one tube. And if you see here, that's what they're trying to show you. Pi times diameter times the length of the tube. So we find the area as 9.4 for the one tube. Then the rest is easy. We just want to calculate how many tubes do we have in total. And in this example here, they had 12, what was it, square foot? That's the sum of the tubes. So how many tubes were there? 75 and 339. Where'd that come from? So the identical surface area, and there are 36 of them. So in this example, there were 36, but we have 6 here. So whatever area you get here, you multiply by the number of tubes. So we have 6 here, and that will give you the surface area for the tube and the heat exchange surface. So let's take this example and do the math. So pi is 3.14 times d, the diameter. I'm going to use the same diameter here, which is 0.25 times the length for each tube, which is 12. That's going to be 9.4 foot square. That's for one tube. And if I have 6 tubes here, I'm going to multiply 9.4 foot square times 6. And in this case, it's different. It's not 26. It's a smaller one. So I'm gonna use my calculator. And it shows here that it's 9 times, 9.4 times 6, 56. So 56 will be my surface area. Pen is gone. 56.4 is my total surface area. So I just do the second example, make sure you understand how it's done, and it will be a useful piece of information to have. All right, thank you. That covers chapter 1. Hopefully you put some comments in discussion boards, and see you next week.